All right, everybody, I think I'll go ahead and get started here. We're a couple minutes late, but thank you for your patience with me. I have a bit of a chaotic first class today, but getting through. I hope you guys are all having a good day and a happy Halloween so far. And hopefully I won't scare you too much with today's work. We'll see how it goes, but we're kind of getting into the heart of the graph theory now, right? I hope you guys are enjoying it a little bit. We're going to have quite a bit to say about graph theory. There is a homework assignment that's due tonight, so feel free to stop by my office hours. Then you can go out for a round of trick-or-treating. You can come back, bring me some of your candy and bribe me for answers to the homework. And that way everybody's going to be happy by the end of the night. And
Can I just give you the whole bucket?
I
That's
think
it?
the whole bucket. Yeah, right. Now everybody's offering. But anyway, no, I will be around though. As my usual office hours, I'll probably take a break though for dinner around 7 o'clock, and then I'll come back. If people want to stop by, feel free to do that. Be happy to talk to you. Yeah, this is the end of October, so we've had. I actually counted it up because I feel like I've been working really hard this month. We've had 10 lectures in the month of October alone, so it's been kind of a long go. In November, we're only going to have 4. Well, excluding we do have one of those we have a midterm, which is another one of the days, but it'll be November is going to feel like it goes a whole lot faster than October did, I'm pretty sure. So I'll get a new homework assignment posted for you for next week, as I always do, to work on. And I'm going to have a quiz in the next 2 weeks. I haven't decided exactly which day yet, so I will probably tell you about that in my weekend email. You know, every weekend I send out an email to kind of give you a preview of the week. The quiz will not be this coming Tuesday though, because that's too soon. But it could be as early as next Thursday. I'll definitely give you an email about that. I just want to kind of look at the schedule and see where we're at. Or it might be the following week instead. I haven't quite decided. So, but other than that, we're just kind of cruising along here. Our second midterm is the class period right before the Thanksgiving break, that week off. And I might as well tell you this now. I'm actually not going to be here for that day. So I will be doing my review sessions the weekend before. And then I'll have somebody else come in and give the exam on that Thursday. It will also, I may as well tell you this now as well. It will take a little while for those second midterms to actually get graded, because I'm actually going to be gone through that Thanksgiving week and not coming back till kind of the end of that following week. So you just have to be patient with me on that. But I will do everything I can to make it as smooth as I can for you. I'll probably over this weekend, I'll probably start getting the resources folder ready a little bit. I mean, we still have 3 weeks, but I'll start getting that ready so you have some stuff to look at if you want to get an early start on it. But yeah, why don't we pick up kind of a little bit where we left off last time? I'd like to kind of do a little more about Hamilton paths and cycles, and then I'll turn you loose on some group work and let you guys practice this a little bit as well for yourself. So on Tuesday, of course, there were 2 main topics we were looking at, which were Eulerian trails and Hamilton paths. Eulerian trails, those are just trails that use every edge exactly once. Remember that a trail is not supposed to repeat an edge. Okay, but if we actually do want to use every edge, then that would mean we would hit every edge exactly once, and that is called an Eulerian trail. We have very easy conditions for this. There exists an open Eulerian trail. I left myself just enough room here to kind of just remind you. Does anybody remember the condition?
Exactly 2 vertices of odd degrees.
Excellent. Exactly 2 vertices of odd degree. And it's easy to check that condition because it's easy to look at the degrees of the vertices. So that's that one. And then what about for a closed Eulerian trail, what's the difference?
All vertices must be even.
Right, no vertices of odd degree. They all have to have even degree. So all vertices have even degree. Exactly. So that's the the sort of the two bullet points here on Eulerian trails. Pretty easy, right? I should also add that the graphs need to be connected. If the graphs are not connected, you're not gonna have any of these things. You won't have an Eulerian trail, you won't have a Hamilton path, none of them. Yeah, Fernando.
Is a graph with one vertex just like vacuously true that it's connected with like no?
Yeah, I think so. Yeah, I think you could say that. Yeah, as a technicality. Yeah, exactly. Yeah, if you have just one vertex, we could say that way. I'm gonna have no idea if Nikolai's confused today. He might be completely lost. I'll have no clue. I'm looking for I'm looking, trying to figure out, the eye contact here.
Maybe sleep.
He could. Okay, I'll keep that in mind. Reminds me of when we were teaching in COVID and I was looking at the black boxes of people. I could barely see anybody out in Zoom land to know what they were thinking about.
You wanna try it on?
Maybe later. I have a feeling it's not gonna work too well for me. But no, that's a cute outfit. Okay, so what was I talking about? Oh yeah, Hamilton path, that's the other idea. Hamilton path, this is just a path that visits every vertex exactly once. And so a path is supposed to never repeat a vertex. But if we want to visit every vertex, then that means we would visit each of them exactly one time. And unfortunately, we do not have any easy theorems, no sort of one size fits all result that will encompass what's going on with Hamilton paths or cycles. So instead, we can try to make some notes about it. And I started this on Tuesday, but I'm going to add a little bit more about this today. The first note is that if you have a Hamilton cycle is just a closed path, right? If you have a Hamilton cycle, then every vertex will have two of its incident edges being used by that cycle. Because you're going to visit the vertex once. So you'll use an edge to get there, and you'll use a different edge to leave, right? So that would be the first idea. Exactly two edges are used by the cycle, but no other edges could be used to try to visit anything else at that point. So you can literally erase those other edges from your graph because you're not allowed to use them anymore. Exactly. So that's the first note. And then we made this comment also last time, which is kind of related to the first point, which is that if you somehow are forced to create a closed subcycle prematurely, by prematurely, I mean before you have visited every vertex by your cycle, then you cannot have a Hamilton cycle that way. So if you were trying to disprove that a graph had a Hamilton cycle, you could, by way of contradiction, suppose that you did, but then you could prove that you would be forced to make a subcycle prematurely. That's actually a pretty common argument. And I'm going to show you how that would look and how we would write it down today. So, and then we're going to practice it in the group work as well. But before we get to that, I thought it might be worth writing down at least a couple of theorems about Hamilton cycles. These are not characterizations, meaning they are not going to be if and only if results, but at least we can do some one-way implications that might be useful. The first one, so I'm just going to say some one direction theorems. And I think I mentioned on Tuesday that this is still very much an open subject of research in graph theory and in theoretical mathematics because the topic of Hamilton cycles is a little bit slippery sometimes. So the first thing I'm going to talk about with respect to a one direction theorem, I actually need a little definition first. So I'll start with a definition on number one here. And then we'll get to a result in just a moment. This is something called the Ore property. So Ore is O-R-E, there's an apostrophe in this as well. This is a mathematician, actually did quite a bit of work in algebra, not just in graph theory, and worked in these things called skew polynomial rings. So if you know a little bit about ring theory, then you might know about polynomial rings, and you can do these twisted polynomial calculations. It's kind of an interesting thing. That's a lot of what I did my dissertation on, and so this is a name that I'm actually quite familiar with in a different context than the graph theory connection. But here's what this says. It just says the Ore property just says that for all pairs of distinct vertices, and also I'll just say x not equal to y. So these are vertices in the graph that are not adjacent. That are not adjacent. The degree of x as a vertex plus the degree of y as a vertex. If you add up the degrees of two vertices that are not adjacent, remember, not adjacent just means there's no edge directly between them. So you might have x right here, and there might be an edge here and an edge here and an edge here, and then here's y down here. X and y are not adjacent, that this should be at least the order of the graph. The order being, just to remind you that is just the size of the vertex set, the number of vertices in the graph, that's the order of G. So this is a property this is a definition. This may or may not be true about a graph. So maybe, yes, it is true that anytime you take two vertices that are not adjacent and add their degrees, it's already at least as big as the order of the graph, or maybe it's not true. But what the theorem says now, and now I'm ready to state the theorem about this. The theorem, which is 11.3.2 in the book, this theorem just says that if G has the Ore property, if the graph has this Ore property, if the property is true, then G does have a Hamilton cycle. In this case, then G, the graph G, has a Hamilton cycle. There's a way to take a path through the entire graph that hits every vertex exactly once. When your graph has a lot of vertices of high degree, it's much more likely that it's going to have a Hamilton cycle, right? You have many more edges to choose from. There might be many ways to actually create this path that visits every vertex. So if you have a lot of vertices of higher degree, you feel more confident that you could create a Hamilton cycle. And this property sort of encapsulates that. Namely, that if you take any two vertices that are not adjacent, and if their collective degrees added together is at least the number of vertices in your graph, then that's enough vertices to guarantee it. Okay. And then, so our corollary, I'll go ahead and just go straight to this next. This, by the way, we're not going to prove this result. This is a big result, like a pretty deep result. I just wanted to get it down for you here. The corollary, which is the very next result, 11.33, it's kind of related to this, just says that if this is a little more, okay, so maybe before I state the corollary, checking the Ore property directly is not necessarily a fun thing to think about doing, because after all, what do you have to do? For all pairs of distinct vertices that are not adjacent, well, that could take you forever, right? There could be lots of non-adjacent vertices that you have to check every such pair. So this corollary makes life a little bit nicer. So what it says is that if every vertex of G has degree at least half of the order of G. This corollary is a pretty easy corollary to understand. If that's the case, then the graph has a Hamilton cycle. Trying to figure out how long it's going to take me to start calling G a group. So I teach 407 all the time. Just doing group theory and we always use G for group. Now we're using it for graph. So does this kind of make sense? If every vertex has degree so if let's say your graph has 20 vertices. Then as long as every vertex has at least degree 10, then you know that G has a Hamilton cycle. It's pretty obvious though, isn't it? Because if you take any two X and Y, each of them will have degree that's at least half of the total order of the group of the graph. And so this Ore property would hold, right? Let's just write that down. This is very straightforward, but it's worth just a quick note. I'll just say for such a graph, right, whether the vertices are adjacent or not, the sums of their degrees will be at least the order of G. So for such a graph, the Ore property holds. Okay, so that's a nice condition that we can use. Maybe I'll just draw a quick example of this. Kind of show you. Again, this is a sufficient condition for a graph to have a Hamilton cycle. It is not a necessary condition. So it's not if and only if. It's only a one-way implication. Let's take this graph here, guys. I'm going to draw a square. 4 vertices on the corner of that square there. And then I'm going to put another vertex in the center. And I'm going to draw that diagonal that you see in the graph there from the lower left to the top right, going through that central vertex. And then I'm just going to connect up that central vertex to one of the other 2 vertices as well. Let's label the vertices here A, B, C, D, E. Something like that. And let's try to figure out. So in this case, the order of this graph is 5. There's 5 vertices here. So if every vertex had degree at least 3, then we would be done by this corollary. Is that true? I don't think so. Vertex E does not have high enough degree, right? The degree of vertex E is less than half of the vertex set. So we can't use that reasoning, but that it may still be possible that the Ore property holds. Okay, so let's take a look at the Ore property. If I take any 2 vertices that are not adjacent, would the sum of those degrees add up to at least 5? So we could ask ourselves that question. So let's take a look at some non-adjacent pairs here. So we could have, let's just start with A here. So A is adjacent to everybody except E, right? And if you add up the degrees there, you get 3 plus 2, which is 5, and that's big enough. Actually, maybe a faster way to argue this is that when you're adding the 2 numbers together, the worst you could do would be to take a 2 here together with something that's 3 or more. So you can see that they're always going to be at least 5. You know, you could do the same thing with B is not adjacent to D, right? But again, this time we get 3 plus 3, which is 6. That's definitely big enough. And you can go through the graph and do all of them that way. C and E, that would be 3 plus 2, which is 5. And that might be about it. So the Ore property holds. So here, Ore property holds. Now, unfortunately, guys, the theorem does not tell you how to make your Hamilton cycle. It just says that there will exist a Hamilton cycle. So we still have to kind of figure out how to do one. Does anybody think they can make a Hamilton cycle out of this? It's always nice to know that it's possible to do it so that you're not worried about whether you're wasting your time or not. This is very easy. You can actually just start anywhere, of course. Maybe I start at A and I go down to D, and then maybe I go over to E, and then I go back to B, and then back to C, and then back to A. That would be just one example. Many other ways to do that as well. But then, as I said, just as a quick remark, this theorem is not if and only if, it does not characterize Hamilton cycles, unfortunately, so I should add that to the record as well here. Again, not anything too terribly deep, but it's worth a quick mention. The remark here is the Ore property is not necessary. It's sufficient, but it is not necessary for a Hamilton cycle. So in other words, it's possible to have a Hamilton cycle without the Ore property. Does anybody think they could draw one? Draw a graph that does have a Hamilton cycle, but which fails the Ore property. Yes, whatever your name is.
You want me to take it off?
No, you're fine, you're fine.
Would it be a really big or large amount of vertices?
Uh-huh,
They all are just connecting around.
a big cycle. Yeah, in fact, it doesn't even need to be that big. I could just draw, I think you could get away with just a 5 cycle. Right? You have this graph, so the order is 5, but if you take any 2 vertices, the degree would be 2 plus 2 is 4, which does not satisfy this inequality. So this graph fails the Ore property, but it does have a Hamilton cycle, which is namely just the entire graph. Right? All of the edges of that graph. Okay, so this is an example to sort of show that that would be false. Okay. All right, so that's one result, this Ore property, nice. I guess we could write down another one that would be kind of obvious as well. Write down a couple of things here. See where we're at. Oh, I mean, obviously, another thing we could say is, so these are results of the form, if we have this property, then the graph has a Hamilton cycle. I can give you theorems going the other way as well. If we have a Hamilton cycle, for example, then the graph must be connected. That's just not even worth being a theorem, but just as a remark, if G has a Hamilton cycle, then G must be connected. So this would be used in contrapositive form to say that if the graph is not connected, then it does not have a Hamilton cycle. That's, I think, fairly obvious. So that's another result. What else could we say? Well, I'm going to give you another condition in terms of something called a bridge. So within a graph, certain edges that are sort of critical to the connectedness of the graph are called bridges. These are just edges that if you were to remove them, the graph would become disconnected. Okay, and there is a theorem about how that is related to Hamilton cycles as well. So let me make another definition here. Got a few definitions today. Again, lots of words in graph theory. It's not a bad idea to have some flashcards to help yourself out with learning some of these definitions. But if there is a if there is an edge in a connected graph G, if there is an edge in a connected graph G whose removal leaves a disconnected graph. So if that actually disconnects the graph, removing that edge makes the graph become disconnected. That edge is called a bridge. It is a bridge within the graph, right? So a bridge is just an edge that would, if you removed it, it would disconnect the graph. So a good example of that might be something like this. You might start over here with having like something like a triangle, and then there's an edge here, and then maybe on the other side you have, I don't know, maybe a complete graph or something on this part of the picture. So this would be an example of a graph where we could identify a bridge very easily. If I remove this edge right here, which I'll draw in blue, a little bit thicker, right? That is a bridge. And I think it should be pretty clear that if you want to have a Hamilton cycle in your graph, you better not have any bridges. Because after all, you know, you start on one side of the picture, and you're gonna have to follow that bridge to get over to the other side. But then if it's gonna be a complete cycle and come back to where you started, you'd have to go across that same bridge again. And to do that means you would be visiting vertices more than once, which isn't allowed. Right? So let's add that as a result here as well. So this is a theorem that's worth stating as well. I'll just put it right here next to the picture that we have. Theorem 11.3.1. You see I'm going a little out of order with the results compared to the book. But it just says that a connected graph, right, with a Hamilton cycle, a connected graph with a Hamilton cycle cannot have a bridge. It cannot have a bridge. There would be no way to, well, I'll just write down the proof, I guess. There would be no way to avoid using the bridge more than once. Because you have to be able to start from one side of the bridge, go across the bridge to the other side, and then you have to come back again. So you'd have to use that edge more than once. So the proof here is just that a Hamilton cycle would have to use the bridge more than once and if you're using the bridge more than once, then you're visiting the vertices that are adjacent to that bridge or that are incident with that bridge more than once as well. Okay, so that would violate the definition of a Hamilton cycle at that point. So a Hamilton cycle cannot exist in that situation. Does that make sense? Does it seem okay? Nice. Okay, perfect. So we've got the idea of that result. But you know, okay, so to be honest with you though, most of the time with these questions about Hamilton paths and cycles in the graph, you're just going to have to brute force it. And I would actually like to do an example of that now. Show you kind of how this works. Let me, so one of the best tools for Hamilton cycles is just brute force. These theorems just are not all that strong. As you can kind of tell, we're not making very deep results here for the most part. The theorems are not all that strong, and the ones that are maybe a little stronger don't apply very often because the assumptions on the graph are just very imposing to where you just can't use the results very often. So let's just do an example of one that we're going to have to. So I would start this on a new page or give yourself plenty of room for this because we're going to draw a pretty big graph. I want to make it hard enough that we actually have to work a little bit to get this, okay? So here is the way this graph is going to look, guys. We're going to have a big giant diamond on the outside. Leave plenty of room though, make it a big enough diamond that you can fill in the middle, because most of the graph is on the inside of this diamond. Okay, and then what we're gonna do is coming on the inside of the diamond, down from the top, there are two edges coming to two vertices in the center. And then there's also going to be the same thing coming out of the bottom. Two edges connecting to two vertices that are on the bottom half of the graph as well, like that. And then I've got these four vertices, you see, that are kind of in the center now. There is a fifth vertex in the center of all of that. Okay, and that center vertex connects to all four of the other vertices on the interior of the figure. So we would have something like that. And then we're gonna do kind of a similar thing on the sides as well. So there's going to, except there's only going to be one vertex, one edge coming in from both sides, but it's very symmetrical. So just an edge coming in from the left side and an edge coming in from the right side. And those vertices that are currently sitting there connect up to the edges, to the vertices on their respective sides like so. So it would be that graph right there. This is the graph I want to have us look at. And now I need to label all these vertices so that we can talk about it. So let's start over on the far left with A. And then I'm going to go straight into the inside and put B right next to A. And then here's C. And then D is up at the top. E is going to be the vertex directly in the center of the whole picture. And then I'm going to go all the way down to the bottom for F. Okay, and then the two vertices to the right of E, on top I'll put G, and underneath I'll put H. And then finally I have I and J over here on the far side. So there's actually 10 vertices.
Missing.
And I am missing K. Sorry, let's make this one K then. I forgot about K. That's going to be K. So they're not really labeled in a very natural manner, but that's okay. Okay, so the question here is basically to try to show that this graph does not have a Hamilton cycle. So let's state that as a question. So prove. Let's prove here, guys. Let's prove that this graph has no Hamilton cycle. That this graph has no Hamilton cycle. That's why I'm like, hopefully going to try to do that much. Okay. So, again, I don't think the Ore property is going to hold, right? I mean, I can find non-adjacent vertices whose degrees don't add up to 10. If there were any bridges in the graph, I could quote that theorem 11.3.1 that says that if there were a bridge, then you can't have a Hamilton cycle, but there's no bridges here. Any edge that I might remove does not disconnect the graph. And so these are kind of, as I said, weaker theorems that are not easy to get a lot of mileage out of. So the way that we generally are going to do something like this is with brute force. And so I'm going to show you how this one works, and then we're going to do some group work and let you guys practice it a little bit for yourself as well. So the idea is to do it by way of contradiction, right? So suppose that there is a Hamilton cycle. Right, and we really want to use, I guess I've erased it already, but we really are going to be leveraging this observation that there cannot be a forced premature subcycle in the graph. Because that's going to say things like, well, then, for example, I can find a subcycle that I want to work with in the graph and say, well, you can't use all of the edges from that subcycle. You can make any subcycle if you find a triangle, if you find a square, if you find any closed cycle within the graph, right? That cycle in and of itself cannot be completely used as part of the bigger Hamilton cycle because it would be premature. So what I'm going to do here, guys, is I'm going to take the big diamond on the outside, and I'm just going to say you cannot use all four of the outer edges of this of this graph, right? So, this, such a cycle, I'll just go ahead and write this down. This is kind of like writing an essay. So you just keep in mind, there'll be a lot of explanation here as we go along. Such a cycle cannot use all four of the exterior edges. Just to be completely clear which edges I'm talking about, I'll go ahead and list them. So there's the edge AD, and then DJ, and then there's JF, and then there's FA. So those four edges around the far outside of the graph, they cannot all be used because that would be a premature cycle that only visits 4 out of the 10 vertices. Okay. Now, of course, that's not the only cycle in this graph. So we could have worked with the one right here and said the same thing. But what I do like about the one kind of on the far outside is there's a symmetry to the graph that sort of said, so we know that we cannot use all of the 4 edges, but you might wonder, does that mean I'm allowed to exclude a specific one of those 4? Or how do I know which of the 4 isn't going to be used? Well, if the graph is symmetrical, if there's symmetry to the graph, which there is, you can reflect this graph right down the vertical axis, for example, or the horizontal axis of the graph. If it has symmetry to it, you can just, without loss of generality, choose an edge that you're going to assume is not used. So let's do that here, guys, without loss of generality. Without loss of generality. Assume, and I'm going to go ahead and just assume that edge AD is not used. Okay, now let me come over to this board because that's going to set off a chain reaction of other edges that either must or can't be used. And what I actually am going to recommend is that we start making a table. Okay, so consider this table. And so I'm going to come over here and make a table of what the options might be. So I'm going to make 2 columns here, and I'm going to make a list of edges that must be used. And then I'm going to make a different column that consists of edges that cannot be used. And when I say used, I mean used by the cycle. Used by the Hamilton cycle, this alleged cycle, which ultimately we're going to conclude does not actually exist. Okay, so we're going to assume that AD is not used. So that would be right here in the cannot be used category without loss of generality. So if you want, you could kind of just dot this edge. I'll just kind of like erase it a little bit. So I'm not going to use that edge. If I do not use that edge, are there any sort of chain reaction conclusions that we could then draw about the cycle that we would have? If there was a Hamilton cycle, we have to visit every vertex. And now we have a vertex here that has how many edges left that are available to use? Only 2. And so we have to use them. If you want to visit vertex A, you must use those edges. That would be AB. That would be AB as well as AF. So I kind of like to highlight the edges as I'm being forced to use them so I know what I'm doing. So I'm going to use both of these 2 edges here. Okay. Now, take a look at vertex B with me for a second. I have to use 2, there are 3 edges incident with B, one of which is already in our to be used list. But we're either gonna use BC or we're gonna use BK. Not sure which one. It's again, a very symmetric graph with respect to this direction. So what we can do is, again, we can do sort of two cases. We could consider both possibilities. So from here, this should be a parentheses brace, but I'm going to do a case one. Right, within my chart, I'm gonna do a case one where I'm going to say, in case one, let's imagine that it is BK that is used. So I'm gonna go ahead for the moment now, and shade in the edge BK. I'm gonna assume that I'm using it. Okay, and let's see where that gets us. So then we cannot use BC because I've used both of the edges that are incident with B. So we remove BC. So that goes in the cannot be used list. Now I have to warn you, at some point, we're going to have to like redraw the graph back to where it was when we took this fork in the road. Okay, so just be aware of that. But BC cannot be used. As soon as BC cannot be used, does that set off any other chain reactions?
Yeah.
C, right, has only two other edges that we have available, so we have to use both of them. That would be CD and CE. So I would recommend some colored markers for yourself on this, just so it's easier to see it. We must use CD and CE in this case, right? So far in this case, we must use that. Okay, perfect. So let's see, does that get me anywhere? I still have to make a choice, huh?
For K, we have to do E, right, because then we would have to sure.
No, that's true. That's true. If KF was used, then we would have a cycle right here, a premature closed cycle, right? So we could put KF in the cannot be used camp. So I'll go ahead and put KF over here. That's right. So therefore we must use KE. So we cannot use KF. So we must use KE. All right. See, this is just, we're just rolling now. We must use KE. All right. And now E has been visited by two vertices, right? So then I can remove EG and EH from being used. We cannot use EG or EH. So EG and EH. Okay, well, let's see. By removing EG and EH, didn't we just force ourselves to use DG and GI and looking at H, IH and FH, right? And I think that's a premature cycle. So let's write all of those down. We must use, what was it? DG and DGI, sorry. And IH and FH. We must use all of those. And at this point, so in this case, we have a forced premature subcycle. And we can just list it out. And we can start it anywhere we want. Maybe we'll start at A. So starting from A, we would go to B. And then I'm just following the blue lines of our graph over there. So from B, we would go to K, then to E, then up to C, and then all the way up to the top at D. And then we would follow the blue lines back down towards G, and then I, and then H, and then F, and then back to A. And you might notice that we almost got it. There was only one vertex, which is J, that we missed. And that's why it's premature. It's premature because we didn't visit every vertex exactly once. So this is a contradiction. Let me just remind you again, I know I said this on Tuesday, but just to remind you again, why is it a contradiction to have a premature subcycle? Well, the thing is that you would, at this point, you say, well, I'm not done yet because I haven't been to every vertex. So then you say, well, I've got to get from J to and from something else. But anywhere you try to draw an edge out of J, you're going to hit a vertex that you have already visited and used all the edges that you are allowed to use. So that's the reason that you can't have premature subcycles in these kinds of graphs. Okay, so that is case one. Then we have to go back to case two, and I think I'll just make my two columns over again here. And so I'm going to need to like I'm going to need to like take off the blue path here for the most part. So I'm going to just erase some of these edges for myself. You guys don't need to necessarily do this. You can either just redraw the graph, or you can just take a picture of this when I'm done. Either way is fine. There's that, I got this. I'm putting all these edges back in again. So this is just to make it look like it did before. And where did we actually, so we already said we're not using AD, we are using AB, we have to use AF.
It was choosing.
We chose BK, so now I'm going to not choose BK. But make this solid, which means I have to choose BC, right? In the second case, so now I have to use BC. I think I have it back to the way it's supposed to be.
Mhm.
Okay, good. So this time for case two, this time we must use a BC. Okay, so we'll put that in the must be used category. So this is the left column is for must, the right column is for can't. And you should be listing the edges in the order that the analysis carries you. Don't decide to scramble up your list of edges over there, or it doesn't make any sense. As long as you have them in the right order, it should be pretty followable. So I'm now going to use BC instead of BK. And are there any other edges that are either forced to be used or forced not to be used? So you see right here, K, we just deleted one of its incident edges, so I have to use the other two, KE and KF, right? So we must use KE and we must use KF. Okay, and does that get us any further then? Maybe let's hear from somebody I haven't heard from yet. Yeah, go ahead, Teresa.
Does that mean you can't use FJ?
Yeah, you see, look at vertex F. I've already got two blue edges here, right? I can only go there once. That means these other edges cannot be used. So I can delete not only FJ, but also FH. They can both be deleted. Right, so you can kind of just help yourself out with the proof is the writing, it's not the graph, so it's okay to kind of mess around with the graph a little bit as you go along. But in the can't be used list, we're going to have FJ and FH. Okay, and so based on that, can we come back to our graph here and say anything else that we would be able to conclude?
Yeah.
What else can I say right now? Maybe somebody I haven't heard from. Kaushik?
You have to use AG.
I have to use HI and what was the other one? HE, right? HE and HI have to be used, so I can add those over here to my list as well. In the must use list, we have HE as well as HI. Okay, so I've filled those in. Anything else we can say right now? Nikolai.
Use CE.
I cannot use CE at this point because E has been visited already, so I'll delete CE. And what else that goes with that? EG, exactly. EG cannot be used. So EC and EG cannot be used. EC and EG. We deleted those. And what else can we say now? I have to use CD. All right, good, because otherwise I can't get to and from vertex C. So I have to use CD. And let's add that to our list over here in the must be used category. So I'm going to go up to make another column here. I must use CD. Okay, who wants to help me with the next observation? One more time. Okay, looking at vertex G, I only have two edges left that I can use, so DG and GI. We have to use both of those. So let's add those to our list over here. DG. We must be getting close. And GI. Oh, are we already done?
Yeah.
Oh, yeah. In fact, we've excluded the same vertex J again. I was gonna say, the other thing is now J, we don't even need this, but you'd have to use IJ and JD. You'd even have a smaller premature cycle just over here on this side of the graph too. So that also works, but this is, this creates, so we have a forced premature cycle here as well. Let's write it down for everybody to see. Sorry, I'm trying to be real good with my camera today. A couple people missing that I know are gonna wanna watch this. So a premature cycle, let's just read it off. If I start at A, then I could go to B, and then to C, and then to D. It's a different cycle than the one we had earlier. From D, I go to G, and then to I. H is next, and then E, K, and then F, and back to A again. Yeah, that looks good to me. So that's a premature cycle. Again, we never did visit vertex J. So it's not a full Hamilton cycle in that case. So that's kind of how these arguments work. I would say this is like, more along the lines of a reasonable difficulty. It can get more complicated if the graph is very big with lots of choices, and then you have cases that require sub cases. Here, fortunately, we didn't end up in that position. Okay. Questions on that? If not, I think I'd like to take a little break from talking and let you guys practice. There are a couple of Hamilton cycle problems on problem 2. And then there's also another leftover graph isomorphism problem from last week's material, if you're interested. You and your group members can decide kind of what you want to do first, second, and third on this. But I'd like to spend a few minutes letting you guys practice for yourself a little bit. So I'll send these around and then let you guys give it a try today. Now, sorry I missed your saw you in Zoom, but it took me forever to get down to class. I did go in there, but I was hoping you were gonna come back.
Yeah.
Sorry, I'm sorry I missed you. Okay. Okay.
You show that the graph is the same, by like checking different properties. You want to. Good.
No, I always do.
It's 7, right?
Yeah.
Yeah.
All right.
Can't just say it is. Prove it.
Prove it.
Prove it.
So A is connected to what, B and
it's too
F, so what's
Oh, we need a picture of Dr. Hannon. Yes.
Oh, wow.
I'll draw you. I was like. 1, 2, 3, 4.
Where's here? It's really.
So,
Yeah, that's why I just take off. And like,
It only has.
That's scary.
Yeah, play basketball. I'm like bigger than my own.
It's like, I don't. So no.
It's good enough. You can drive it.
The first section.
Yeah, I think one of the M3. Just right there, it's actually part of the. Four and
I would like
three.
other stuff that
Really?
No.
Very similar. Yes, they do it just kind of.
They just have more floors. Oh, no, never mind. Oh, that's confusing. Okay.
Yeah.
This.
I know, I wanted to change the results.
like, I had teacher, I had.
We can check like the. I see a 3 right here. Three, like.
Oh, yeah.
Does that one have a 3?
And then the highlighter. Like the laser tool too.
Yeah, bro, the only marker I get, look at this. Okay, cool. Oh, you want it? I was gonna put a base on.
Yeah. Yeah.
Am I right to do
So that. Oh, wait, is that already? Oh, we have to, that's not even, that's, we have to. Yeah. I don't think. Oh, yeah. There, I mean, have to be AB.
I know, it's about here.
So we got, that takes a break, like if you, there is or some like. We have to use those and those are the ones free.
So they're setting zippers.
I want to go be.
Oh, there's a-
So the next one.
Yeah.
Oh.
Wait, isn't this already?
Well, no, one of them is not, okay, the one I have is not.
Because you can't switch. So there's no way to get to the other ones? No,
But I thought. Because I
You remember? Like.
Right.
Use it.
Oh, right, yeah.
To say that AC is not used.
Yeah. And then. Yeah, get back up here. You're gonna end it. See if it's not there. Let's do it how.
Then you have to use a B and a G. Absolutely. Yeah, I think you have a choice. I think you're just about to get to the contradiction. Exactly. Exactly. You guys get any pictures there?
Yeah.
You're gonna. Don't, right, okay, so,
This one.
my question, why is that without loss of life? How do I know I don't?
So. Actually, there's not.
These already.
I was using that in the one I did earlier because it's ignorance rates. So I'm. I'll pay for the actual thing. So not me, right? I mean, I think I would say that maybe we say, no, let me see. That's right. So you can say. If you're. This. Then, of course, you have to. It's not. Oh, okay. Not AC, that's fine, so that's case, right, so that's, okay, so we're maybe not done today, right? This is one case that we don't do AC. It's got a premature, any cycle out of it. Although. Yeah, I think that. I was trying to think. I guess. If you're using GH, you also have a picture. But yeah, I think you can do another case where you use AC. Yeah, okay, try. Symmetry, yeah, exactly. So I would, like, if I said I want to use AC and AB, that would be symmetric with using AC and BC. So you don't have to do both of those cases. Okay, anybody need a answer check or some help or anything? Yes, I have. It may be necessarily incorrect, like, so how come we can, how come we're saying we must use the. Oh, I see, you have to, but you're using. That's not where you're starting. You said I'm going to use AZ and AB. Right, so then you have to use, you actually have to use this one and this one and this one and this one, right? So those four, and then you have this one also. And so then down here, right, you'll either use this edge, which would make it create a sort of slice, or you will use this edge. Which then, I don't know why you would use HI. I guess because you're using HI, those are the two edges there. Clear,
Yeah.
but this is like one case, there's another case where we. You're starting off with saying, assume. So you're saying without loss of generality, assume that AC was not used. I would say that's not without loss of generality. No. If I don't use AC, then of course I'm gonna be using. The edges that are indicated here, but, right. I think. You have to go back and do another case where you say, what if I did use it? Cause it would be it'd be a totally different. I would say this is great for the first case for the cycle, but I think there's another case. Yeah, exactly. Yep. Does anybody else need a hand? So probably next case I would like you have this graph that's on. Yeah, it's a very good. I mean, I don't have to do this specific to the graph, but sometimes I can't fix the changes. And the search. Yeah. Arbitrarily just. you're all checking it like that. But if you sell it, like that's
And then.
totally different process. This class. I have to create examples that are sufficient and just to sort of. But not so difficult that there's been this sort of example. Is a thing for making more visitors.
So we really should say that you want to look at who makes the building.
Yeah. That would be, so is it track or not, or Marion Trail or not? We're doing the way it's now. Characteristic number, is this another one, on all?
To be honest, I didn't.
Exists on. Yeah, I think it would be a hard, you know, that's. I could see that that was. I don't know what. If it's got an inside. Yeah. Yeah.
Wait, so it's.
So we can not.
That's why you should have it. Looking for a different. I didn't mean it. Honestly, it was just here. When we going. Right, but then I just think that just like. Because doesn't seem you to go somewhere. I'm thinking it's like. And then 18. Right?
What you mean?
I do. So I know you did. The third stage. Yeah, but this is just. Oh, yeah. Very true. We got waiting. I think that's good.
Yeah.
So we should needs to be. Okay. Or.
So if you choose AC, here's where we can do it without loss of generality. If you choose AC, then you cannot choose both of these two ends. Because then you'd have a cycle right away, right? So without loss of generality, maybe you don't need it. Now you're off and running. Now at this point, you'll have to use this edge and this edge and this edge and this edge. And before long, you'll close up that cycle bit.
I think though, like.
It's really the symmetry of the picture, so here the left and right. So if all I've said is that I'm going to pursue some steps, then I know that I can not use both of these, and because it's symmetric across the central axis, that's where I'm using the symmetry.
Yeah.
Did that today or even yesterday? I've almost every day. So I put them for days. Really systematic and sort of like stress. Think about. We get times in that meeting. Only thing is. I can't complain with it, that's for sure, that's for sure. Did you guys get that personal work done? This out, okay? Yes. Recycling, and that does not. Oh, yeah. So, I admire your dedication here, I will tell you, it's like psychic, so. And this coming up to so you may. Well, maybe you wanna share the, that wouldn't take very long, you can just draw it. That'd be great. Feeling pretty fat, these are not as, these are not as, because of the bigger spaces, or because of the. You can try that, but if it doesn't work, all I'm gonna say is, well, you just didn't figure it out. Okay. Much better to just find a structural problem. Because that, this will probably lead you into a bunch of cases that could hard to. But anyway. Sure. Sure. Hey, guys, we are at 5:15. That is the finishing hour, and I don't want to hold you up from your trick or treating. So, I'd like to just wrap this up. The solutions to this are online, so I hope you will look at them when you have time later on. And I wish you a really nice rest of your Halloween. Don't eat too much sugar in the next day or two. Dennis will be seeing you soon if you do. And I'll be downstairs if anybody's got any questions about anything from the homework that's due tonight. I'll be happy to give some hints on that. Thanks, great. See you next time.
He's like, wait, hold on, what?
What's up?
It's his fault.
Did you guys get pretty far on this thing?
It makes more sense to me when we create it. Modern like. Because how you.
Oh, yes, same.
I was wondering why he think like AD.
Alright, well, I will see you.
If it's with
Next
like after doing the work and silence.
Go home. What? Sorry. Go. I get to go home.
Yeah, I need number 20. I think I know one too. I literally asked so many people and no one knows number 20. Yeah, I think.
Was that the MS1?
Yes, it might assume.
Yeah.
Are you the one that, you're the only one? Okay.
Okay, bye, Heath. Thank you for being here. I have not quite decided yet. I will probably decide that in time to let you know on my weekend email. You know, every weekend I send an update what's going to happen the next week. So I may decide about that by this weekend and send you all an email so you can start studying. Okay.
I was like, it's the third group works ever since the midterm one, so it's gonna be a proper time for quiz.
Yeah, I think it's about time for a quiz. So it might be next week on Thursday, probably not on Tuesday, but maybe on Thursday next week we have a quiz. But I'll let you guys know for sure on the weekend.
Alright, thank you.
Okay, yes, of course.